Hi everyone, this is Mr. Bozade, and I'm going to work through problem number 2 on worksheet 10. So let's dive in. It says that a frictionless pulley, which can be modeled as a 0.8 kilogram solid cylinder with a 0.3 meter radius, has a rope going over it. The tension in the rope is 10 newtons on the right side and 12 newtons on the other or the left side. What is the angular acceleration of the pulley? So we know our goal here is to find alpha, and a good place to start is to write out our net torque equals I alpha equation. So our goal here would be to find alpha for this problem. So let's start by thinking about what might be the net torque that's acting on this disc right here. Well, we know that on the right side we've got a force of 10 newtons of tension in this wire, and on the left side is a force of 12 newtons of tension in the wire right there. So we can use those two forces to find the torque, or the net torque. We know that those two forces are going to ultimately apply a net torque that's going to rotate and rotationally accelerate our disc this way, which is counterclockwise. So let's say counterclockwise is going to be our positive direction. So the torque of our force tension on the left will be positive, and the torque of our force tension on the right would be negative, in which case. So let's write that out. Positive torque of force tension on the left side minus torque of force tension on the right side is going to equal I of the disc times alpha. So let's see. Let's take a look at these two forces and their torques. And when we take a close look right here, what we see is that both the forces of tension are perpendicular to the radius. And that is true for a wire or a string on a pulley at no matter what the angle is that the wire or the string comes off the pulley. No matter what the angle, it's going to be perpendicular to the radius of the pulley. So we see that in this example for the force on the left, but we also see it for this more simple example for the force on the right. Just because of the simple fact that a pulley is a circle, that means that the force of tension of the wire will be perpendicular or 90 degrees to the radius of the pulley. So that means we don't have to worry about sign of the angle of that force with regards to the radius or how perpendicular it is. It's entirely perpendicular. So we can go ahead and write out our torques as force tension on the left times the radius minus force tension on the right times the radius equals I of the disc. And since it's a solid cylinder, we can model that as 1/2 mr squared for the rotational inertia and times alpha. Now if we take a look, we've got values for everything. We've got values for this force on the left, the force on the right, the radius, and the mass of the disc. So our only unknown is alpha, so we can go ahead and we can solve for that. So let's go ahead and plug in our values. And then we can solve for the angular acceleration. And the angular acceleration of this solid cylinder, or this pulley, comes out to be 16.6 repeating radians per second. There you go. I would say one of the more important things that we thought about in this problem is how the radius is relative to a force when we're looking at a pulley. And what we discovered is that no matter what the angle that a wire is coming off of a pulley, that force is going to be perpendicular to the radius simply by the nature of the fact that the pulley is a circle. All right, I hope that was helpful, and I will see you later.